Okay, section 2.3, video number 2. Let's find the domain and range of this function, but instead of ordered pairs or a mapping, I have a graph. So again, the domain is the set of all input or x values. So if you look at this graph, your x values go from -4 all the way over to 4. So you've got every number in between there on this graph. So this is going to be an interval. So the domain, if you'll remember what we did with interval notation, is going to be -4 to 4 square brackets because those numbers are included. So you can tell if I follow the circle of this graph, or the ellipse as it is, I'm taking on every x value between -4 and 4. It's not possible to get, x equals 6 in this particular function. So only the value is -4 to 4. Now, if you look at the range, those are the y values. It looks like they start at -6. They go all the way up the axis, and the highest number I get is 6. So the range of this graph is going to be from -6 to 6. Okay? So domain -4 to 4, range -6 to 6. And you get just by looking at the graph. Now, in this class, the only time your intervals will ever include y values is when I ask for the range. All the other intervals I'm asking for will be on the x-axis. Let's look at this particular one. You may not be able to see it, but this has arrows on the end of it, okay? So what this means is this line keeps on going forever. So there's no particular part where my x values start. This graph keeps on going. So x values are going to be at -infinity. So my domain for this guy is -infinity to infinity. That always has parentheses. Same thing with the range. The range, if I try to start down here, it keeps on going forever. So -infinity to +infinity for the range. So the range is -infinity to +infinity. So again, just looking at the graph, finding out where your x values are and your y values. The set of all x values is the domain. Set of all y values is the range. Let's look at this particular graph. This is a quadratic. It's a parabola. We'll be graphing these a little bit more later. But if I were to continue the graph here, it does this. That's what it keeps on going. So let's find all of its x values. So if this graph keeps on going, my x values continue all the way over here and over here as well. So this has a domain of -infinity to infinity. Now, if I go find the range, it's not the same case. There are no y values down here. So my y values don't start until I get to, what, -3? So that's where the y values start. But once they start, they continue going all the way up to infinity. So the range is from -3 to +infinity. So it includes the number -3, and then I always have a parentheses around infinity. Now, one agreement, unless we specify otherwise, the domain of a function, of a relation, is going to be all real numbers, okay? So unless I tell you specifically, if I give you some kind of agreement like x + 5 or something like that, just assume its domain is -infinity to infinity. Now, something we want to do graphically to determine if a relation is a function is something called the vertical line test. So if I look at a graph, I should be able to look at it and tell if something is a function or not. So if you look at this, we saw this a moment ago. These are just simply the 4 points, okay? -1, 1, 1, 2, 0, -1, and 4, -3. We know it is a function because when I look at the x values, there are no repeated x values. Another way of telling that if it's a function is just to draw vertical lines, okay? If I draw a vertical line through each of these points, I only hit 1 point, okay? If I had hit 2 points, it would not be a function, okay? So when I draw vertical lines and I only intersect my relation 1 time, that makes this a function, okay? So what would happen if it hit two places? Okay, if I hit this scenario, this would mean negative 4, 3, and 1, excuse me, 4, negative 3, and 4, 1. That's what it would mean. It would mean 4, negative 3, and 4, 1 on the graph. It means repeated x values. So that's what this vertical line test does for you. It tells you when or not you are hitting the graph at two places. If you hit the graph in two places, you've got repeated x values. So this one is a function. Now let's look at the graph of the next one we just did. Here, if I draw a vertical line, they drew it right over here at x equal negative 2, and they found that it hit the graph in two places. So this is negative 2, 6, and negative 2, negative 6. Okay. So when you look at those 2 points, you see repeated x values. Okay. You didn't have to get those points to figure this out. If you can just draw a vertical line and it touches your graph more than once, not a function. So this is not a function. Let's look at another example. Here I have a straight line. You should be able to see no matter where I draw my vertical lines, I can draw vertical lines all day long. It's only hitting that graph one time. So this is a function. Let's look at the next case. Here you have this parabola we saw a moment ago. I can draw vertical lines, continue to draw vertical lines, and each vertical line only hits the graph one time. So this is a function. Let's look at an example of a graph. Let's just do one for example. What if you had a graph that looked like this? So in this case, if I draw vertical lines, it would hit the graph in two different places. So this would be not a function. Okay. So again, if you can draw vertical lines and that vertical line only touches your graph once, you have a function. Touches more than once, not a function. So they're saying decide whether this is a function or not, and give the domain and range. We're going to be doing some graphing later, but this one's pretty basic. Y equal x plus 4. So y equal x plus 4, that's a straight line. So I can just pick some points. If x is 0, y is equal to 4. So 1, 2, 3, 4. Okay, if x is 1, y is equal to 5. 1, 5, right here. If x is 2, y is 6. Something like that. So what you see is this is just a line that goes through these 3 points. Okay. So if I draw vertical lines to test this, every vertical line is only hitting that line one place. So this is a function, and it's a straight line. All of your straight lines are going to have the domain negative infinity to infinity and the range negative infinity to infinity. So in this case, it is a function. It has a domain of negative infinity to infinity, and it has a range of negative infinity to infinity. So every line will have those same domain and ranges, and any line is going to be a function. So again, when we talk about functions, remember our definition, there are no repeated x values. So if you're looking at a mapping, it means that for every element in the input, there's only one element in the output. Again, in sets, it's no repeated x values. On a graph, you draw vertical lines, it only intersects one time. So those are ways that we can tell if something is a function or not. What we want to do next is to move into something called function notation. Okay, so for example, if I've got the line y equal 3x minus 5, what we think about that, we think of y is my dependent variable. We think of x is my independent variable. We also think of your x as your input. You think of y as your output. Now, what we can do, we can write in function notation. We will say that y is a function of x. And we're going to make that notation, we just call it f of x equal, in this case, 3x minus 5. So what that means is f is a function of x. And that function says you take x, you multiply it by 3, and you subtract 5. So think of it as a rule. You know, f is a rule. You give me an x, and the thing I'm going to do with it, I'm going to multiply it by 3, and I'm going to subtract 5. So f of x is just another word for the y variable. Okay, so you should get very comfortable seeing something like, if I write y equal 3x minus 5, f of x equal 3x minus 5. Those really mean the same thing, okay? Y is 3x minus 5 is a line, and f of x equal 3x minus 5 is also that same line. So it's just a notation that we're using for that dependent variable y. So how do we find things like, what is f of 2? Okay, that means I want you to substitute a 2 in for x. So if f of x is 3x minus 5, then f of 2 is 3 times 2 minus 5. That's 6 minus 5, which is 1. Okay, so we write that f of 2 is 1. So we would say f of 2 is 1, or f at 2 is 1. Okay, so those are just ways of substituting in for function notation. So again, same thing, y equal f of x equal 3x minus 5. So y is our dependent variable. This is our expression that defines the rule we're doing. F of x is just a way that we're denoting this function. So when we put it in that notation, we're assuming that it is a function. So f of x is a function of x. So I have a function of x defined by 3x minus 5. So we're going to see that a lot in the rest of this course. Now just keep in mind, f of x doesn't mean f multiplied by x. Okay, I mean, before you might have seen things like, you know, xy equal xy. That's algebraic multiplication. That's not the same thing here. Math is very famous for using the same symbols to mean different things. So when you see, you know, something like this, you know, f of x, you know, g of x, this is just function notation. Okay, so it means you plug x into f, you plug x into g in order to figure out what these values are. So let's look at an example real quick. F of x is negative x squared plus 5x minus 3. Gx is 2x plus 3. Find f of 2. Okay, so f of x equal negative x squared plus 5x minus 3. Now, I'm asked to find f of 2. What I'm going to do, let me just write f, and I'm just going to write open parentheses. So everywhere you saw an x, I'm just going to write a parentheses, okay? So all I did was I took this first definition of f of x, I just rewrote it, and everywhere where there was an x, I just left a blank space. Now, in order to find f of 2, you're just plugging 2 into that equation, okay? And typo here, that was a squared, okay? So if I evaluate this, I get, this is negative 4 plus 10 minus 3, which is equal to 3. So f of 2 equals 3, okay? And so what that tells me, this is my x value, that's my y value. So I know that the point 2, 3 is on the graph of that function, okay? So 2, 3 is an xy coordinate for this function f.